Good morning, everyone. This is Gayatri Shirisagar, Assistant Program Manager for Pune Knowledge Cluster. Thank you for joining the most exciting talk in India SNT 75 at the rate 75 series. This is the 9th talk in this series. Pune Knowledge Cluster and Indian Academy of Sciences started this series last year to mark India's 75th year of independence. And we have several talks which you can see on our YouTube channel. Today we have with us Professor Deepak Dhar, who received a prestigious award, that is a Boltzmann medal, recently. And this is the 9th talk. Today we also have with us Professor Ajit Kembavi, who is the principal investigator of the Pune Knowledge Cluster, and he is also former director of IUPAP. I request Professor Kembavi to introduce Professor Dhar. Thank you so much.
Thank you very much, Gayatri, and good morning to all of you. I'm very happy to welcome you to this talk by Professor Deepak Dhar, who is one of the most distinguished theoretical physicists in India at the present time. He obtained his BSc from Allahabad University in 1970, so which puts him in a long line of very distinguished people who are emerged from that university, and which has also included an astronomer, Professor Goenka. I remember in 1980 and was there until he superannuated and moved to ISER Pune. So he just moved from Mumbai to Pune and as a distinguished visiting professor since 2016. He works in the general area of statistical physics. As a fellow, and the famous work that he has done in phase transitions will be the subject matter of his talk today. And then he is a fellow of INSA, all the 3 academies, and the Third World Academy of Sciences. And he's got very good, many distinguished prizes, and the Bhatnagar, including the Bhatnagar Award, the S.N. Bose Medal, and most recently the Boltzmann Medal of the International Union for Pure and Applied Physics. And that was in 2022, this year. And I'm very happy to say that he's the first Indian physicist to have got the Boltzmann Award. So now I'll not say anything more, and I invite Professor Deepak Dhar to begin his talk.
Thank you very much, Ajit, for your very kind introduction. So in this talk, the overall title of the series is India in 75 years, which is a little bit forbidding. But what I will try to do is I'll try to keep some historical perspective. And I will try to pick one small part subject and try to give you the, I have worked in this general subject, and I'll try to describe this. I will omit the technical details, and I will give the general flavor of the subject. And I hope that even people in BSc and can follow the basic point. And so let me just start. So this is the general plan of talk. I will start by defining what are fractals and what is their effective non-integer dimension of fractals. It is possible that some of you already know this, but for completeness, let me just spend a few minutes discussing this. Then I will discuss, not discuss in detail, but mention the work of Wilson and Fisher, which provides the background for much of this work. And then discuss what is called epsilon expansions and axiomatic epsilon expansions and constructive epsilon expansions. And then I will, as an example of this, I will discuss self-avoiding works on fractals, where you can calculate the critical exponents. And then there is some sort of, given any particular problem, you have to find out what's interesting about it and recognizing the key elements of the problem. For me, this realization came somewhat late, and that's kind of a story I will share with you and then summarize in the end. Okay, so let us start with fractals. So many of you have seen the word fractals before. Some of you have seen pictures like what I show here before. The left-hand picture is what is called the Mandelbrot set. And the right hand side is usually called the Julia set. And don't worry about the names. And so what is the characteristic feature which is common to these kinds of pictures? Okay, so the fractals are characterized by some kind of repetitive structure. And there is a second thing which is not actually fully there in the first picture. It is there, but it's not obvious, is that you can actually define something called a effective dimension, which is the non-integer for these fractal objects. So what is meant by non-integer dimension? So we all know that a line is a one-dimensional object, a surface is a two-dimensional object, and a solid object like a cricket ball is a three-dimensional object. So that is the usual notion of dimension, and which we will keep, like we will give some, we'll generalize and extend this notion so that the dimension can be non-integer, but the line will still have a dimension 1, a surface will have dimension 2, but you can construct some other object which has a dimension between 1 and 2. Okay, so, but to get to this point, let us first start by asking, how do we know that the world we live in is three-dimensional? So I think when I've talked to various people, they usually say that you need 3 coordinates to specify a point in a three-dimensional space. So it is three-dimensional. But this point cannot be used. This is correct, of course, but it is not enough to specify the dimension of space. So this is a simple point, but let me explain it for all of you. So suppose you take a square which has a side 1, then each point can be characterized by 2 real numbers, x and y, which give you the x and y coordinates, and they lie between 0 and 1. But now suppose I write the decimal expansion of x and y. So I've taken an example. I've taken 0.7358 for x, 0.9243 for y. Then any decimal expansion will correspond to a real number between 0 and 1. But if I take these 2 real numbers x and y, I can construct a single real number by intertwining the digits of x and y. So I take the first digit of x, then the first digit of y, then the second digit of x, second digit of y, third digit of x, third digit of y, and so on. And you get a number like 0.79325483 and so on. So it's very clear that for each pair of real numbers x and y, you get a single unique real number, and vice versa. If I know this number, I can get back x and y. So specifying a single real number, which is on the right, I can uniquely specify all the points in the plane. And so there is a one-to-one correspondence between the points on the plane and a single real number, which gives you, for example, the points on a line. So we cannot use the fact that you need 2 real numbers to specify, to define what is a two-dimensional space. So what do we do? So what one needs to do is some structure which is more than just the points in space. Right now, what we said was there is some points in space, and each point you need to specify the coordinates of a point to specify a point. But you need a little bit more. You need to know which point is near other point, and if this extra part, it says that this is endows the space with something in mathematics they call it topology. So given a point, there is also a neighborhood of a point, other points which are near this point. Okay, so for this, actually you don't need fully the distance, but let me go a little bit further and say that given any 2 points, we also know what is the distance between points. And then one can construct a set of points which are within a given distance epsilon from a given point. So that is called a sphere or ball of radius epsilon around that point. I've written it here, radius r. So define a ball of radius r as the set of points which are within distance less than or equal to r from a given point. That point will be called the center of the ball, and the ball is the set of points. Now, in this ball, there is a set of points which is the boundary of the ball. And it is clear to us that if you take a 3-dimensional ball, the boundary is a 2-dimensional surface. And so you start with a ball in n dimensions. and I want to know which is the dimension n I'm in. I don't know of n. Then I'll construct the ball, I'll construct its surface, and first determine the dimension of the surface, and then add 1 to get the dimension of the ball. How do I determine the dimension of the surface? Using the same method. Now you take the surface and construct balls of radius epsilon within the surface, and iteratively you can determine the dimension of the space, because at one point when you go to a one-dimensional line, then there'll be only 2 points at the boundary, which will be a distance epsilon from the given point, and then we say it's one-dimensional, and this defines the dimension of the space. If you work in 15-dimensional space, it will tell you inductively that the dimension of space you started with is 15. And this will continue to work in the first example I gave before. So I didn't use the real numbers to specify, I used the notion of distance. But this dimension of definition of dimension is still an integer. You cannot get a non-integer using this definition. So we need to do something else. And this is slightly more complicated, but this was already done by Hausdorff around 1930. So Hausdorff suggested that there is an alternate definition of dimension. This is done using covering a set of points by balls of radius epsilon. So I've shown a simple picture below. So you have a square. You want to cover it with balls of radius epsilon, which are denoted here by small yellow discs. So you try to cover means all the points should be covered. If I only use the yellow disc the way I've shown, then you don't cover all the points. But if I add the pink on top, then I actually cover all the points. And that is called covering of the space with points. I will have to add more pink balls than I have shown here. But anyway, that is the general idea. And then you ask how many balls are required to cover this space. And then you can cover with more balls, but what is the minimum number of balls required to cover the space? That is called n of epsilon. And then if you decrease epsilon, how does n of epsilon change? It will increase. How does it increase? It diverges as epsilon goes to 0. And if it diverges as a power d, then we call the d the dimension of space. This agrees with the common notion of dimension in the cases 1, 2, 3 that we discussed before. Okay, but now you can take this other object which I show here, which is called the Sierpinski gasket. You take a triangle, an equilateral triangle in 2 dimensions, and remove the points in the middle inverted triangle. And then iteratively you get smaller triangles, you keep on removing this. So this is called Sierpinski gasket. Now I can try to use this definition of dimension on the set of points which remain after I've done this iteration infinite number of times, levels. Okay, so then it's easy to see that if you take the whole triangle, you can cover it with a single ball. But if you take the size of the ball to be half the previous size, then you need 3 such balls to cover. And if you take it 1/4, then you need 9 such balls. So in general, you need 3 to the power n to cover with balls of radius 2 to the power minus n. And so the dimension of the space is log 3 to the base 2, which is 1.58, which is non-integer. So now you have a system with a non-integer dimensions, and you can construct spaces with slightly different from this construction and get other fractal dimensions. Okay, so now I will like to discuss why we want to study phase transitions on fractals. So this idea will not be introduced fully well, but anyway, it was introduced in a landmark paper by Wilson and Fisher in 1971. And the first page is shown here. It says critical exponents in dimension 3.99. And it says they calculate the critical exponents for dimension 4 minus epsilon, where epsilon is very small, and do something. So let me just give a background. In the renormalization theory of critical phenomena, there is something called universality of critical exponents, and very different systems show the same critical exponents. And the critical exponents depend only on some parameters like the nature of the transition order parameter and the dimension of the system and symmetry of the order parameter. Okay, so they depend on the dimension. So, but anyway, what exactly is the meaning of the title here, critical exponents in 3.99 dimension? So if we consider dimension d equal to 4 minus epsilon as a continuous variable, and critical exponents are functions of dimension, and you assume that you can Taylor expand the exponent as a function of epsilon, then they have somehow calculated it to be whatever result is given there. Okay, so what Wilson and Fisher did, they considered a self-interacting scalar field phi, and it is some so-called P phi field theory in D dimension. Please excuse me for being a bit obscure here, but I'm just trying to give you a flavor of that thing. So even if you don't understand it fully, it is perfectly okay. You will understand the later part, even if you don't fully understand what I'm saying here now. So when they do a perturbation theory for this P phi theory, you get integrals of this type, integral dtk 1 upon k squared plus lambda squared. Some integrals are involved in the perturbation theory which you have to evaluate. Okay. Now, if I write integral ddk, which is the integral over all space, as ddk as k to the power d minus 1 dk, where dk is the real number, and sd is the volume of coefficient in the volume of d-dimensional sphere, then this integral can be formally, then it's a real integral, and you can think of this integral now as a real integral with k varying from 0 to infinity, and then the d can be taken to be a real number. And so one analytically continues this d to arbitrary real numbers, and for each d you can evaluate this real integral, and then they do some further analysis, and they come up with this answer that the exponent gamma is equal to 1 plus epsilon by 6 plus more. Okay, but one can still ask that is this equation 1 gamma equal to 1 plus epsilon by 6, is this an equation or is this a definition, where the right-hand side is defined by the formal manipulations using the analytical continuation? You say that if you replace this integral by that, and then you evaluate this, and then you take this approximation and do this and this is the answer I get. But what is gamma? Is it defined by the rules to calculate it on the right, or is it defined a priori in some other way before? Normally, one would expect that there is an Ising model, and you can calculate its susceptibility, and it has an exponent gamma, and then you can calculate it. It's not defined by the right-hand side, it is defined independently. Okay. Anyway, so this was an interesting question, and most of the time people take the right-hand side as the definition of the left-hand side, which doesn't make it an equation, it makes it a definition. So Wilson discussed this issue, what is the spaces of non-integer dimensions? And he wrote down some axioms. These, the spaces have to satisfy this set of conditions, and then all the things which you do later are true. And, then you can evaluate this and you get this result. However, people have studied these axioms further, and they find that they are not self-contradictory, but they lead to difficulties. For example, you can, using the axioms, you can say that, okay, here is a space, then I construct the set of points which are at a distance 3 from given set of points. Then the volume of the space you calculate, it turns out to be negative using the rules of calculation given. But it makes no sense to have the volume negative. So, then you can say, what can I do? Spaces in non-integer dimension have non-positive volume measure, but it is not very nice. And so it makes it very difficult to understand what this could mean. But anyway, in 1975, 4 years later, Nelson and Fisher wrote a paper in which they actually calculated the free energy of an Ising model on an explicitly constructed fractal, the same fractal I showed you before. They take the sides of this fractal lattice, put an Ising spin on each, and they calculate the partition function, calculate the specific heat. And unfortunately for this Ising model, they found there is no phase transition. Phase transition occurs at t equal to 0. So you cannot define critical exponent gamma, but at least you can show that the susceptibility diverges as exponential of j by t as t goes to 0. Please just notice that when t is 1 by 10, this number is huge. So, but anyway, it doesn't have a regular phase transition. However, what one has here, there is an explicitly constructed fractal where one can determine exponents directly. So I take some other model in which the Ising model has a finite temperature phase transition, then I will be able to calculate gamma there and then compare with things like epsilon expansion techniques and see how the formal analytical continuation works in the same way. So we can use different recursive constructions to generate different fractals. They have different fractal dimensions and see how these exponents vary with dimension. So here is a simple example of a variation of the previous construction. I start with a graph which is shown on the figure A, just 4 points. And so I will think of this as a triangle with 3 corners and some stuff inside. And then I take 10 copies of this and join them up in this way as shown in figure B. Okay, now I have a new graph in which you have 3 corner points and some stuff inside, and then join 10 of them in the same way recursively, and I get a new graph. This graph also has 3 corner points, take 10 of these and join them up again and so on, and make a graph which is infinite in size, much bigger. Okay, so this is the recursive construction. It is called given Mandelbrot family of fractals. It should be Mandelbrot. And the starting graph is here, the second, okay. And this picture is if you take, in this triangle, you can take B triangles on a side. Here it is shown for B equal to 4, but you can generalize the construction for B equal to 5, 6, and so on. And the fractal dimension of the graph easily is checked, is log B into B plus 1 by 2 by log B, because, B into B plus 1 by 2 is the number of triangles you need to use. And divide by log B gives you the fractal dimension. But, so I can take this and I can study critical exponents on these families of fractals and see how the exponent changes when I change the dimension. So that is the idea. Okay, so now we are given some lattices, but we want to construct problems in which you can actually get some critical exponents right. So this idea was very nice. So I thought one can take a fractal and study some other model. Ising model is not working very well because it doesn't show a phase transition. Can I take some other model? So the simplest model people have studied in the past are called couple oscillators. Mass is connected by springs. So it is shown here. And in this case, it turns out that you can actually take this coupled mass model and construct all the normal modes and study the density of normal modes and then calculate the partition function. Okay, so then there is a classical divide theory of solids which is usually taught in undergraduate classes. And it turns out that if you take these solids and you use quantum mechanics, then at low temperature, the specific heat varies as T to the power D for low temperatures in solid in D dimensions. In 3 dimensions, it goes as T cubed. If you do the same calculation in 2D, it goes as T squared. So in this case, I have calculated all the density of normal modes for this fractal. And I can ask what will you get as the specific heat at low temperature. And it turns out that the specific heat at low temperature goes like T to the power D, but this D is 2 log 3 by log 5. And then you can say this is the effective dimension of the fractal, which is different from the fractal dimension we defined using the volume, the Hausdorff dimension of the fractal. So this dimension, I had called it the effective dimension, but later Ramal and Toulouse called it a spectral dimension, which is a little bit more explanatory because it says that it's defined in terms of the spectrum of normal mode excitations. Okay, and okay, so let's go on. So now we would like to construct some other models where you can study critical exponents. So on the harmonic solids also don't undergo actually any phase transition. At zero temperature, the specific heat goes to zero in some way, but there is no real phase transition. So I wanted to construct some stuff in which there is a phase transition, and it turns out that a simple problem where you can get phase transition is self-voiding work. Okay, so one model that shows phase transitions is the self-voiding work. So what's a self-voiding work? Self-voiding works are works on a graph. You start at a point, go to nearest neighbor. From the nearest neighbor, you jump to its nearest neighbor, and so on. That is called a random walk. But there is a constraint that if you have already visited a site, you cannot visit it again. So it's called self-voiding walk. And these are on regular lattice, you can also construct self-voiding walks. And then there are models of long chain polymer in solution, because if you take a polymer chain in solution, it takes a conformation like a random walk, except that there is a excluded volume interaction and the same site cannot be, the walk cannot come back to itself because there is already something there. Okay, so this is the lattice. It's the same lattice as we drew before, but I've drawn it schematically to emphasize the fact that what we look for is points and they are connected by neighbors. And the fact that there was an embedding triangles doesn't matter. You should just say that there is a point, it has 3 neighbors. And if I go to this point, it has 2 other neighbors. If I go to this point, it has other neighbors and so on. So there is a set of points that are connected to each other by nearest neighbors. In this case, we will connect them by springs. And we will just construct a random self-voiding work on this and see what happens. So here is a picture of a self-voiding work on this, starting from this black point. You can go to this side and then to this side and then to this side and so on. And so this is a walk which has 1, 2, 3, 4, 5, 6, 7, 8 steps. It's an 8-step walk. I could make some other walk of 8 steps, but if you start at this point, there's only a finite number of walks of n steps you can make. So we can say, let Cn be the number of self-voiding walks of n steps. So C1 is 3, and C2, let us go back up. If I start at this point, how many 2-step walks I can make? From this point, I can go to 3 ways, but from next point, I can go to only 2 other ways. So there are 6 ways, and so on. So for any finite n, you can determine Cn actually explicitly by just brute force counting. But if n is large, then how does this number change with n? You can show that this number increases exponentially with n, and there is a coefficient gamma in front, which is, there is a power in front, which is called n to the power gamma minus 1 traditionally. And this power is something which is the same if you take different lattices in 2 dimensions. So, it is called a critical exponent for self-voiding walks. Similarly, you can calculate mean end-to-end distance for walks of n steps n. Maximum possible length is n, but the typical length is not, it doesn't increase linearly with n, increases as a smaller power. And this power is called nu, it's called the Flory exponent. And what is the value of gamma and nu for my fractal? If I change the fractal, the gamma and nu will change. So it turns out that this gamma and nu can be calculated for these fractals. For any finite b, you can calculate it exactly. But in the limit of large b, you can show that 1 by nu has a formula of this form. Okay, and so so it tells you if nu is when b is very large, the dimension becomes near 2. So this is in dimension 2 minus epsilon. The critical exponents behave like this. Okay. So these answers, which you can get exactly, do not agree with the results obtained using the axiomatic approach of Wilson, because the fractals we use do not satisfy all the Wilson's axioms. So for example, Wilson says that the space has to be translationally invariant. On a fractal lattice, all the points are not equal. So, it doesn't, whatever treatment Wilson uses cannot be used. And it's not very clear what we should do. Anyway, so the behavior is complicated. It cannot be characterized by a single parameter like the effective dimension. And cases in which the fractal has not finite number of corner vertices, but a bigger number are harder to study. Okay, but now let me make a digression. And so we were just calculating all the kinds of critical exponents for fractals. And it turns out that you can also study the behavior of other models. And in general, what one has is that there is a finite number of coupling constants. And when you go to a bigger size fractal, bigger level, then there is equations which you can determine the coupling constants of the higher order graph in terms of lower order graph. And you get equations like this. G are some coupling constants at the level r+1. There are some functions of GR. And these recursion functions Fi can be calculated explicitly. But sometimes this Fi can be very complicated. For example, this self-avoiding work on fractals, which we discussed before. Suppose B is large. Then F is an integer polynomial which of some degree B squared by 2. And the coefficients of the polynomial will also be very big. They may be like 10 to the power 5, even for B equal to 5. And if you go to bigger, they can be much bigger. So even if it's a polynomial equation, it looks very messy and difficult to study. So just, don't be scared by this. I wanted to show you the structure. So if you study the problem of branch polymers on fractals, the same fractal family for K equal to B equal to 2, Knežević and Vanemenus, they wrote down that there are 6 variables, A, B, C, D, E, F, and they have recursion equations which look like this. And by staring at these equations and analyzing their structure, you will be able to determine the behavior of the branch polymers on this fractal. But the equations look bad, but this is B equal to 2. If you go to the B equal to 2, then the equations are much more complicated, and you will perhaps need 10 pages of this such field with very thin, big stuff. And the coefficients which involved in the polynomials are also big. So they used a computer program to generate the recursion equation for B equal to 3. And but even the computer in 1985 could not work for B equal to 4. It was too big. The CPU time required to generate the recursion equations was beyond the capability of computers at that time. I guess if you work now, you may be able to do for 5, 6, 7, but not much beyond. But an interesting point in their analysis was that the results seem to be independent of the details of the recursion equations. So even if you change the recursion equation, the results did not change much or didn't change at all. So this brings the interesting question: can one get the exact critical behavior without writing down the recursion equation? So this question interested me. So I saw this paper in 85 and I couldn't see how to make much progress, but kept thinking about it on and off, not all the time, but now and then. Till in 2005, I realized that the key to the solution. And the key is actually very simple once you get it. And I will explain the idea here, but it leaves you with this question: why couldn't I have ever thought of it before? Why did it take me 20 years to realize this simple point? But this, I can just say that this has been said by many other people many other times. Given a problem, there is one way to solve it. And in the end, the solution is quite simple, but it may take you a while to realize, and then you get the answer. So let's just go on. So let me take some simple recursion equations. A prime is equal to 10 a cubed b square, b prime equal to 3ab. So you start with some values of a and b, and you calculate a prime, b prime, then use these a prime, b prime to calculate a double prime, b double prime, and so on. And the question is, what will happen? So the answer is that if you start with small values of a, b, the results goes to 0. If you start with largest values, then they go to infinity. But then there is a critical point in between where the things will actually go to infinity, but in some critical way. And so that's what we want to understand. How does it happen at the critical point? But if you look at these equations, you can say that log A and log B are linear functions of log A prime and log B prime are linear functions of log A and log B. And so, after many iterations, the solution is of the form log A and log B go like lambda to the power R, where there is a 2 by 2 matrix, which I can read off 3, 2, 1, 1. And its largest eigenvalue will determine the rate at which log A will grow. And then, that determines the behavior of how these things will grow. But these answers don't depend on these 10 and 13. Even if you change these, the growth will be the same. Okay, so this result can be extended to polynomial equations. So instead of 2 variables, suppose I had 5 variables, but they were like this, that log A was a linear function of the logs, then they will still be the leading behavior, which will not depend on the coefficients. Oops, okay. And so these A prime and B prime grow as exponential of R. But now, suppose I add other term to this, plus AB squared here. It doesn't matter because, A is very big and A cube B squared plus A squared B squared is the same as A cube B squared. So it turns out that if you have many terms in the right-hand side, one can drop subdominant terms without affecting the asymptotic behavior. And in lucky cases, you keep only one term in each. There is a huge polynomial with million terms on the right. You just keep one term. If it's a dominant term, then you will still get the same answer if you didn't drop all the other terms. Okay, and so this is what I managed to do. So this is the first page of the paper. It's not any very important paper, but I'm so fond of this because it took me 20 years to realize this simple point. Okay, so it says that take this given Mandelbrot family of fractals and you study branch polymers, then the number of polymers grows like lambda to the power n exponential b n to the power psi. I cannot determine what is lambda, I cannot determine b, but psi there is an exact formula for, which is not given in the abstract. Okay, but it's given in a table here. So let's not worry about the details of this. You can determine the psi exactly for this for all values of p. There is an explicit formula. So let me just summarize here. So the study of phase transitions on fractals is an interesting reason is to understand the influence of geometry on critical behavior. So it turns out that, in 1 dimension, sometimes there is no phase transition. In 5 dimensions, there is, and so on. So there is some dimension below which phase transition doesn't occur, above which it occurs. So why does it happen? It is understood in terms of the connectivity of the space. And so, you have a connectivity of space on the gasket and on 2D, and they are different. And how does it influence the critical behavior? This is the general question. So on fractals, if you have the kind of structure which I showed, where at each level there is a finite number of corner sites, it's called the finite ramification. Ramification means branching. Then you have exact renormalization equations, and they can be studied exactly without approximation. You determine the exact answers. And I pointed out that, there is this axiomatic epsilon expansion, which was pioneered by Wilson and Fisher. But you can actually study these explicitly on fractals, and that is called constructive epsilon expansion. And it gives different answers. Then you can pick your own. And then I will just give you an example of, in some cases, you can simplify the problem if there are so-called dominant terms, and the answer becomes simple. Even so, you don't need to know everything about the problem to be able to say some things interesting about it. And I will stop here. Okay.
Thank you so much, sir, for this wonderful and insightful talk. We request participants, if they have any questions, they can put it in the chat box. If anyone has any questions, please put it in the chat box so that we can take it in this Q&A session.
They could simply raise their hand.
Yeah, or the...
Any questions?
Yeah,
Yeah.
I think Ojasvi Sharma has raised the hand. I just unmute her. Hello, Ojasvi, you can talk now.
Yeah, hello. Good morning, sir.
Mhm.
So my question was that this fractals thing, which you said that it's basically depending on the geometry of the system, that the transitions will depend on the geometry. So is this the concept of fractal, is it like lattice point, which is not real, but it's just imaginary in our head? Or is it something which is very real, which we can observe in molecules?
Okay, so the notion of a lattice is that there are a set of points which are connected to other points by what we call nearest neighbor bonds. Okay, now are they real or not? I know that there are real materials like copper which form a lattice. To that degree, the lattices are real. The point is, they are the atoms of the lattice. They are, and there is one atom which is like a spherical ball, and there are other balls near it. Now, I don't want to worry about all the structure. I represent the ball by its point and a neighboring ball by another point. So a lattice is a representation of a real system. It is a mental construct. It is not by itself real. But the lattices are there in real world. That is what I'm trying to tell you. Is that satisfactory?
Oh,
Ojasvi, is it, did you get your answer? Yeah. I think, sir, there is another question by
I see
Srijit.
that, yeah, but Ujasvi has not answered.
Yeah, I'm not sure.
Okay, let's go to
Srijit is the next one who raised the hand. I just unmute him. Yeah, Srijit, you can go ahead.
Hi.
Hi.
So my question is about the stretched exponential you had towards the end of the talk. So for exponential scaling, there is some intuitive picture that we have from, say, if it is a time series, there is a loss of memory over time, or if it is a spatial thing, it's correlations breaking, getting weaker with distance. So is there some intuitive picture that one can keep about stretched exponentials?
Yeah, so what happens here is that the starting point is that the number of animals goes like exponential in n times and exponential in n to the power psi, where psi is less than 1. So if you convert it into a generating function for the same problem, it leads to essential similarities in the generating function of the type exponential plus 1 upon x minus xc to the power nu. Okay. So, in fact, the reason for interest in the branch polymer problem was precisely because here on fractals, you seem to get stretched in, these exponentials. But on the normal d-dimensional integer lattices, you don't get these exponentials. And so what's so special about them, or why are they not there in the standard problem? Unfortunately, all the proofs of all these results, the mathematical proofs can show that the number grows exponentially, but they cannot generally rule out a sub-leading n to the power psi kind of behavior. And nobody has been able to prove that, for example, in 3D, the number of animals has only a power law correction and not a stretched exponential correction.
Okay.
Srijit, hope you have got your answer.
Yeah, but by the way, we are not able to unmute ourselves, so I think Ojasvi was not able to.
Yeah, if the participant can raise their hands, we can unmute them actually. Otherwise, it will be disturbing others. So we are taking each question at a time.
So ask Ojasvi, unmute her and
Yeah,
then
yeah.
ask
Ojasvi sent a message that she got her answer.
Okay, very good.
Yeah. Does anyone have any questions? So they can raise their hands. Yeah, I think Ojasvi has again raised the hand.
So my question.
Yeah.
So my question is,
Hmm.
so my question is about the dimension thing, which you said that the different notion of dimension. When you constructed a square and you tried to cover it with circles, and but there was another case where you were trying to cover up the equilateral triangle with the pieces of triangles. So, but the definition which you gave about the from the Hausdorff was to cover it by the spheres or the disk of a radius epsilon. So why we were using triangles to cover a triangle?
Okay, so it is not using triangles. You can actually, those triangles are balls in that space. There is a point such that all the points in the triangle are equidistant within distance epsilon from that point, like that.
Okay. So then why it is not a square in the square space?
So that depends on the, so one should just recognize that we are working with minimal notions of distance. The distances are always integers. They are nothing in between because we only go from one side to next side to next side. Okay. So whatever is from a given side within distance R is called the ball of radius R. And whether it looks like on a regular square lattice, it will actually look like a diamond. So I will say a diamond is a two-dimensional ball. That is the usual mathematical usage. I'm not making up some confusing jargon.
Okay, sir. Thank you.
Okay.
Are there any more questions?
Yeah, Pardeep, this was, I think, some one question is there.
Just a minute. I think someone also raised the hand. Again, I think it's Ojasvi. I think Prateep Bishwas, he asked a question that, sir, you told about self-similar fractals. Is there non-self-similar fractals? If yes, how we find its dimension?
Okay, so the definition of dimension which I gave is applicable even where there is no exact self-similarity. You just have to say take smaller balls and see how does the number of balls increase. And so you can take similar constructions like what we discussed, but say that take a triangle, put 3 points on 3 sides of the triangle and make an inscribed triangle and remove the inscribed triangle. But the 3 points don't have to be the midpoints of the original sides. Then you get a construction which is still recursive, but it will not be exact self-similarity. So, you can generalize this construction in other ways. And so a lot of people have studied such fractals, and all the natural fractals don't have exact self-similarity, but they have this basic structure. There is self-similarity in the small epsilon limit.
Yeah, thank you, Professor Dhar. I think that was the last question. We can request participant to, switch on the camera so that we can screenshot and.
Oh, a few things is that I would like to thank Deepak for a wonderful talk that he gave. It was rather technical, given the nature of the series, but nevertheless, that so many questions are being asked means that the talk has been absorbed. And so one needs these kind of talks and one needs this kind of an audience. And I think it has been a very successful attempt. So thank you very much, Deepak.
Yeah, I wasn't sure. I looked at 1 or 2 previous presentations by other people and decided that it was not very technical, but it was a little bit non-trivial, I guess, still.
Yeah. So, but
necessary. I didn't want to waste everybody's time by saying something which everybody knew already.
Yeah. So, but the fact that so many people ask so many questions means that it has been absorbed, which is a great good thing. Hopefully, people will be inspired to work like you. Thank you very much.
Thank you.
So we request participant to turn on their camera so that we can take a screenshot, and this will be available on our social media handles. Yeah. thank you, everyone. And this talk will be available on our YouTube channel in the next week. So you can watch if you have any questions, or if you want to go back and see the information. Thank you once again. And we'll have similar talks in the upcoming months. The details will be available on our website. So you can be touching with us on pkc.org.in. Thank you so much. Thank you, Professor Dhar, and thank you, Ajit sir, for joining the talk today. Thank you.
Thank you, all of you, for joining.
Thank you, all of you.
Thank you. Thank you so much. We'll close the session now. Thank you.